So welcome. Thanks for a huge turnout. It's awesome. So I'm Brandon Rubenstein. I manage the mechanical and thermal team for Microsoft's server development. And this is Husam Alissa. You can introduce yourself.
Yeah, hey, I'm Husam Alissa. I work for the Microsoft Data Center Advanced Development team.
So great topic. There's a lot of very cool liquid cooling stuff going on today. So I'm just going to do a quick intro, and then I'll let Sam talk about all the stuff he's spent a lot of time working hard on. The point of this presentation this morning is mostly concentrating around the adding to the flexibility of the Olympus platform. So what we've done is we've spent a lot of time investigating liquid cooling potential solutions for Olympus in order to expand Olympus's flexibility and ability in general. And a lot of the stuff you're going to see here is kind of shown again in other liquid cooling presentations. So I'll go ahead and hand it over to Sam.
All right, thanks, Brandon. All right, so as Brandon mentioned, we'll be doing a quick review of liquid cooling technology, all based on the Olympus platform. We'll dig into where the chip side is going, what the infrastructure wants or needs or can be updated, and then we'll dig into some liquid cooling technologies retrofitted to Olympus Blade. The Olympus server happens to be pretty easy to work with and adapt with different liquid cooling technologies, and that's something we'll be showing today. As Rolf mentioned, there is the Advanced Cooling Solution work group in OCP, where there is a session or a team on door heat exchanger, cold plate, immersion cooling, and we encourage people to participate and provide their feedback. All right, so just quickly going through some market research data. We're going to talk about the processors and we'll talk about GPUs. So in summary, I mean, obviously we're looking at trends where the power of the processors is going up with time, and we're already exceeding or going above 200 watts on the processor side. And from a thermal engineer point of view, what happens is with the die power is increasing and the case temperature requirement is usually dropping as well. Typically, we have limited resources when we want to work with TIM1 and case, and hence the innovation most of the time has to happen from the junction and higher, and this is where, whether it's cold plate or immersion or any of these solutions can help. From the GPU side, so we're showing the NVIDIA V100 300-watt chip or card, and to the bottom of it, we're looking at Microsoft G50 expansion box with 8 of that cards and a 4-kilowatt chassis. We're all aware of the recent or announcement by NVIDIA about collapsing 16 cards in a. This is an example of about 10U unit, I believe, and this whole thing is basically a fan wall. So if you look at the holistic, just looking from combining server side, software stack, and infrastructure side. So yes, I mean, liquid cooling can enable density, but we like simplifications as well. And the thing is, right now we're building data centers that are airside economizer, just bring fresh air from outside. So got to compete with that. And obviously the ultimate data center where we have plumbing and dry coolers, this is what liquid cooling can bring into the equation. From the efficiency point of view, obviously the elimination of either to minimize or to eliminate the fan power overhead, either from the server or from the infrastructure. And because the ability of being able to reject higher quality heat, that means we can be climate agnostic, deploying data centers in Dubai or Amsterdam. And the third prong to this is what we discussed, is basically the chip side. So the trends of increasing powers, but also the potential of making interconnects closer, whether it's on the motherboard or on the network stack. So what we're going to show you today is all based on Microsoft Olympus Blade. So you're looking at the Olympus Blade with the local and remote heatsink design, in this case supporting 205-watt Skylake processors, the fans, and obviously we have that space at the rear if you want to embed more storage hardware. So this blade is already 1 kilowatt capable air cooling, and it's a pretty efficient blade as well. So the fan power overhead is pretty low. So what we will walk through is implementation of liquid cooling on Olympus. All right. So this will circle back to what Cam Turner was showing you earlier today about implementation of cold plate to Olympus Blade. So what we're seeing here is the implementation of CPU module, so cold plates, DIMM module, FPGA module, and M.2 module with dripless connectors. So just kind of to summarize this, the typical loop of the coolant is going into the DIMMs, the M.2, the processor, half of the center DIMM, and then back, and then similarly the second loop. So what we're showing here is some data, and let me do this. I'm trying to get a pointer. All right. So this chart basically is showing the junction temperature for the processors. So what we did is basically a perturbation where we changed the water inlet temperature through ASHRAE W1 to W4. And there is also a perturbation on the GPM. We're not showing that here. So we're just basically showing that the air-cooled unit is at 85 Celsius. And when we start implementing the cold plates, so at W1 we could bring the junction down to 43, and at W4 it could be 72. And those kind of two ends of the spectrum, either to enable more performance on the chip, or save on leaking current on the lower end, or go to the higher end and basically enable dry cooler operation. So that's a decision to be made. And obviously, in parallel to that, how much heat is being captured by the coolant loop will vary. Now we also care about serviceability. So for any of the liquid cooling technologies to actually go through, we need a serviceability model that is at least as effort-taking as our air-cooled racks or easier. So what we're showing here is, so Project Olympus Blade already has a blind mate power connection, our PMDU unit. What we worked on here is we added a manifold that is dripless and blind mate, so with guidance connection as well. So ultimately, we are able to, let's see if I can play this. Are you guys able to see a video or no? Let me do this really quick. Yeah. So basically blind mating power and cooling at the same time. All right, so we're moving from hybrid cooling technologies. Now we're going to start talking to immersion. So the cold plate technology enabled us to eliminate a bunch of fan power. Now the next step is to zero out on fan power, or fan in the chassis. So what we're showing here is Olympus implementation in blade level immersion. So we're basically bringing immersion to the blade and maintaining the rack vertical infrastructure. That's kind of one of the main benefits to this kind of technology. In summary, dielectric coolant pours into the high density components first with walled heat sinks, and then pours to the rest of the chassis. And I can play the video if I make it smaller. It's kind of a quick showcase of how this works. So the dielectric initially comes or pours down the heat sinks, then pours over the rest of the motherboard, which enables us to use minimum amount of fluid that could be expensive as well. Now the technology after that is obviously still talking about single-phase immersion, but bath level immersion. And again, this could be hydrocarbons or other flavors of one single immersion fluid. In this case, we're showing an implementation where Olympus was updated. Basically, the main thing we did was to add indium foil just for chemical compatibility for this kind of fluid. Serviceability is something to consider. Dealing with viscous fluids is something to also think about. Your technician would have to be dealing with such fluids. And kind of to summarize it, or the final technology I'm showing today is, I think you guys were able to see a demo of that today as well, which is two-phase immersion called Project Olympus Blade. We have the demo at OCP, and again, we're happy that a lot of technology leaders are implementing their technologies on Olympus, and we're happy that Olympus is an easy platform to work with. So obviously we have boiling, low boiling temperature fluids, and that basically controls that gives you a lot of ability in heat transfer, but also a trade-off because you could lose that fluid. It could be costly, so you need implementation to mitigate that. Here we're just quickly showing the implementation of boilers on Project Olympus Blade and some data on reduction of junction temperature between air and this kind of cooling. Now again, this will be a function of what flavor of fluid do you use and what's the boiling temperature. Okay, so we have a lot of time remaining. Okay, so in summary, we showed you a bunch of implementations of liquid cooling to Olympus Blade. Basically, this just adds more ability to Olympus on cards and future generation chips. But there is also an important thing that we need to take into account to enable any of the liquid cooling technologies. Whether it's, for example, if you're talking cold plates or the hybrid technology, the cost is a big deal. Uniformity of specs, and this is what OCP is trying to do. Open specs on DIMMs and FPGA modules, on dripless connectors, so on and so forth. Leakage mitigation is also a big deal. We're going to have water glycol basically inside the servers. And that's something to take into account. For immersion, same applies. Cost consideration of whether it's tanks or blades that are enclosed, CDUs, and all that kind of secondary fluid considerations. As Rolf pointed out, certification is a big deal. And this can go twofold. So components, whether it's capacitors, motherboards, fiber, network, we will need certification of these components rather than have basically a new experiment every time you want to try something out. And the same applies for geographical regulations and moving fluid around. Another thing about immersion is there's a typical claim, and I think it's credible to say a bunch of challenges of air contamination can be eliminated. Yet we don't have statistically significant data that shows the merit of immersion on actually statistically significant samples. That's another thing needed. Major spillage and disasters, that is a big consideration, definitely. Liquid management, shipping, handling, going between different geographies. Liquid health check, lifespan, and quality check. And the point that applies to everything is redundancy of sources for all these technologies. That's an important thing. This is why we're saying less proprietary and more commoditized. Another consideration is variation in density. Not everything is a high-power CPU or GPU. There is also supporting storage and network infrastructure. How is that gonna be laid around in the data center? Other considerations are on the packaging side. So basically, to make use of the merits, for example, of immersion, packaging of the motherboard, laying out between the processor and the DIMMs is something to be considered. And the same applies that we need some alignment between the chip manufacturers and the ability of these liquid cooling solutions. And again, we encourage you to join in the Advanced Cooling Solution Group, whether you're interested in all these technologies or some of them. Again, having open specs and a lot of people on board make this technology more accessible. Thank you.
Sam left us time for questions. So
Yeah. Go ahead.
To what degree are the specifications on like your blindless manifold and the single-phase immersion, are you submitting those specs to OCP?
So we expect that there will be a couple of different sources for that stuff, Dale. So there will be whatever comes out of the Open Rack Blind Connect. We'll absolutely look at that, very seriously. Part of the other effort that we're looking at is how Olympus combines with Open Rack, and Open Rack will be looking at these things as well. So there's a couple of those avenues, and obviously there's proprietary solutions as well that. If they have some cost realities to them, we can entertain those as well. But obviously, Microsoft is heavily supportive of the open community, and that's the angle that we'll try and maintain.
Which of these are you guys interested in trying? Which do you think is the most closely ready to go in your data center? Which should you try next?
Yeah, so we're not going to commit to anything, but the way I see it is liquid cooling really needs to be driven on a technology front, because from a CapEx standpoint, it's always higher. And so eventually we'll get to the point where some of these chips or the GPU solutions will drive us to require liquid cooling. When if the data center is not ready for that, or the infrastructure is not set up for that, obviously a rack level solution makes the most sense, because it's something you can just drop into the space that you're already doing liquid or air cooling in, and so there's no extra infrastructure that goes along with that. There's some costs involved, but as we mature and we kind of settle on what the liquid cooling technology that makes the most sense is, there's bugs in all of these systems, right? And we're all working to figure out how to work those bugs out. That kind of evolution, we'll have enough time to decide what the final most effective solution is, and then the data center can adapt, out there. So we're talking, rack level liquid cooling probably in a couple year time frame, and then this more mature solution 5-10 years out, probably. The whole data center goes under?
Undersea data center, Project Natick.
We're absolutely looking at immersion, right, as Sam showed, but there isn't a commitment to any one technology yet.
And the one you're referring to is the underwater data center?
Oh, the underwater data center, yeah. That's another interesting solution. Actually, the interior of that data center is air-cooled. Mm-hmm. So, but all of this stuff could go into that kind of data center as well, and then you have a nice heat exchange process there also. Yep.
It was a good presentation, Husam and Brandon. So it was a good review too. I understand that Olympus is a very good project, and that's the current technology. You mentioned that for all of the technology, cost is the major factor, and you also mentioned about different considerations for computing and packaging and other things. So my simple question,
They absolutely need to be prepared for it. So two things will drive liquid cooling. The first is that there's no technology in air that can remove the heat from that heat flux from the component. And that one is kind of cost independent. The technology is forcing that. Then the other is the TCO. And that TCO is data center level all the way down to the chip. And that's always an ongoing kind of analysis and effort to figure out, when it makes sense and what technology makes sense and that kind of thing. So yeah, as far as roadmap goes, I can't give you much direction on what Microsoft's looking at, but we know today Olympus is, as we showed, up to a kilowatt per U, and so we can easily do 40 kilowatt rack with air. So it's not really a high rack power density problem. It's a flux problem on the chip today, anyway.
Rolf, go ahead.
You mentioned CAPEX always being higher. Can you elaborate on that? Because I'm assuming that by comparing it to a rack, you mean a full data center TCO?
So yeah, true. So
Just would like to have that context.
right, sure. Yeah, so at a rack level, removing the air cooling stuff, putting in liquid cooling stuff costs you money, right? But you're right, facility level, you have some costs that you're taking out as well. Yep. Okay,
All right.
thank you.
Thank you.